This is the Chapter 9 review. Section 9.1 of this chapter had to do with the transformation or the movement called reflection. Reflection, you work across a reflecting line on a coordinate plane, and so the shapes reflect across that line. And we talked about 4 different types of lines of reflection. We talked about the x-axis to figure out the ordered pair. When you reflect something over the x-axis, you leave the x alone and take the opposite of the y. If you're reflecting over the y-axis, you leave the y alone and take the opposite of the x. If you're reflecting over the origin, you take the opposite of both the x and the y. And if you're reflecting over the y equals x, you switch your x and the y value. I suggest that you change your points algebraically before you put the pre-image and the post-image on the coordinate plane. So here's an example of a reflection. You have the triangle ABC with these vertices, and I've graphed those up here. And I'm going to reflect it over the origin, which, based on what we just looked at, remember, reflecting it over the origin, you take the opposite of both the x and the y. So I'm going to change the points first, and then I'm going to put it on the coordinate plane. So you have A prime becomes positive 2, negative 1, because I take the opposite of each one. B prime becomes 0, negative 4. I can't take the opposite of 0. C prime becomes negative 3, positive 2. Now I have the reflection over the origin that will graph this. So I'm going to graph the point 2, negative 1, which is A prime, 0, negative 4, which is B prime, and negative 3, positive 2, which is going to be C prime. So this right here is reflecting this about the origin. So essentially it moves it or changes it, rotates it 180 degrees. All right, we also talked about lines of symmetry. Lines of symmetry are the line that you cut down or through something that you have the same shape on both sides. So if you folded it up, you would have the reflection of the side. So this one has exactly one line of symmetry, which would be, right through here if I drew a straight line through there. So it has one line that you could fold it up and have the same thing on both sides. It has no points of symmetry because I can't rotate around any point and get the same figure. This does have point symmetry because I can rotate. Actually, I could rotate, 90 degrees, 180 degrees, or 270 and have the same figure. You also have lines of symmetry that go this way, this way, this way. Oops, I missed that center. And this way. So if you will, there's 1, 2, 3, 4 lines of symmetry. The next transformation we talked about was translation. Translation is like a slide. So you're adding to the x value positively if you're going right, negatively if you're going left. You add to the y value positively if you're going up, and negatively if you're going down. The translation can be expressed in words or symbols. So I might write this out, translate the image 2 left and 4 up. But that can also be expressed as x minus 2, or x plus a negative 2, and y plus 4. Here's an example of a translation. If you'll notice that I did it with symbols. So I'm actually going to add a negative 2 to the x, and I'm going to add a negative 2 to the y. So my new points become negative 4, negative 1, negative 2, positive 2, and 1, negative 4. So I'm going to graph these now. I have negative 4, negative 1, which is your A prime. I have negative 2, positive 2, which is your B prime. I have 1, negative 4, which is my C prime. So you can see what we've done is we've taken the green shape and we've moved it 2 left and 2 down. Then we talked about rotation. Now rotation can be done using a protractor and a compass and done it by hand. It can be drawn using a combination of reflections, but my recommendation is use the information in section 9.7 on page 508 to effectively graph these using the rotation matrix, okay? And I've got one of those done out. Same triangle that I've been using, ABC, and I want to have a rotation that is counterclockwise by 90 degrees. Well, this is the 90-degree rotation matrix. This is your X, Y, X, Y, X, Y. So if you will, this is A, this is B, and this is C. So what you're going to do is you're going to take your calculator, and under, hopefully you can see this, I'm going to go to the matrix, okay, and I'm going to edit the first one. I want it a 2 by 2, so let's see, 0, -1, 1, and 0. Okay, so that's that matrix. Then I'm going to go in, and I'm going to edit matrix 2, and I want a 2 by 3 matrix, and I have -2, 0, 3, and I have 1, 4, -2. Now, then I'm going to get out and I'm going to select matrix A times matrix B, and it has to be in that order, okay? And I'll press enter, and this is what I'm going to get as a result. I'm going to get -1, -2, -4, 0, and 2, 3. So this is A prime, B prime, and C prime. Okay, now it has to be this times this, because remember this is a 2 by 2 and this is a 2 by 3, and the middle terms have to match. So now I can just graph that. I have -1, -2, which is A prime. I have -4, 0, which is B prime, and I have 2, 3, which is C prime. So what I have done is I've rotated that green triangle 90 degrees counterclockwise. Then the fourth kind of transformation we talked about was dilations. Dilations is expanding, which is enlarging, or contracting, which is reducing, an image or measurement on a coordinate plane, not plan, by a given scale factor, often denoted by the letter R. If R is greater than 1, then the image is expanded, or it gets bigger. If R is greater than 0 or less than 1, then the image is reduced, so this is going to be a fraction. If R is equal to 1, the image is just duplicated, so you have the same image. This is accomplished by multiplying each component by the scale factor. So here's an example of that. Again, same triangle. I want a dilation of 1/2, which means what I'm going to do is I'm going to multiply each one of these points, each X and Y, by 1/2. So this is going to become -1, and this is 1/2. This is going to be 0, and this is going to be a 2. This is going to be a 1.5, or 3/2. And -1. So I'm going to graph, these are my prime. So I have -1/2, which is going to be A prime. I have 0, 2, which is going to be B prime. And I have 1.5, -1, which is going to be C prime. Now, the truth of the matter is, this often looks like it shifts it some. It's not carbon copy on the line. So don't think when you do this that you've done something wrong. Sometimes it shrinks up in it, depending on the numbers. 0 always throws it off. All right, 9.6 has to do with vectors. Remember, vector is an array that has both magnitude and direction. You got to be able to express a vector in component form, giving the tip and tail vertices. Remember, I always go tip to tail. That's very important. So I want the component form of vector SR. This is my S coordinate. This is my R coordinate. Now, obviously, the R is underneath the tip, so this is the tip. So I'm going to start here and go backwards. So I want to know the difference in the Y and the X's. So -2 minus a -4. And I have -3 minus 5. The answer to these are going to give me my component form. So that's going to be +2. And this is going to be a -8. So that is the component form of that vector. Basically, it tells you if it was in standard position what that vector would look like. Remember, standard position means the tail of it is on the origin. All right, I'm going to find the magnitude and direction of the vector that I just had. Okay, now I graph that vector. Okay, so this is the graphing of that vector. I can use the distance formula to find the magnitude of it. So I could say d is equal to the square root of, so it's going to be the difference in the x's, so -2 minus -4 squared, plus the difference in the y's, -3 minus 5 squared. And that's going to give me, this would be a +2 squared, which is 4. This would be a -8 squared, which is 64. So I'm talking about the square root of 68. So that would be the magnitude of it. You could also use Pythagorean theorem by finding the component form first. So we already did that. So let me go back and grab the component form of that. That component form is 2, -8. So if I take the component form and put it in the Pythagorean theorem, those are the two sides of my triangle, if you will. The easiest way to see this is if I triangle it out. Okay, so there's this, oops, I think I went one too many. This should be right there on that. Sorry about that. There we go. Okay, so look at the blue, not the green. Okay, so my x value here is 2, so I'm going to say 2 squared. My y value here is going to be, I can say -8 or 8 squared, and that is going to give me my c squared, or my hypotenuse squared. So I'm going to have 4 plus 64, which is c squared, or c is equal to the square root of 68. Okay, same thing I got here. I just used Pythagorean theorem, though, on my component form. So that's telling me that's that length right there, or the magnitude. Finding the direction is a little bit harder. You're going to shift your x and y to some degree. So basically, I can look at this, and I graphed this one wrong too. Okay, so it should be -4 or 5, which is right there. So again, I'm going to switch it to the blue color. Okay, so I want to know what this angle is right here. Okay, so I know that this is a 2 and this is an 8. So I'm going to do, and that's tangent, so I'm going to go the inverse tangent of opposite, which is 8, and adjacent, which is 2. So if I take my calculator and go inverse tangent of 4, I'm going to get a 76 degrees. Now, what I need you to recognize is I am going to shift my x and y axis so that that puts that vector in standard position. So in other words, the tail of the vector is on 0. So it really isn't just the 76, even though that's what I have right there. It's going to be, all the way around is 360, so I'm going to take 360 minus my 76. So 360 minus 76 is going to give me an angle of 284 degrees. Now, here's your little cheat code. Okay, I figured out what the angle is. Okay, we're going to call the angle theta. Okay, if my ray is in, or my vector is in the first quadrant, then the answer is simply my theta. If it is in the second quadrant, it's going to be 180 minus my theta, because I'm going to go backward the length of my, or the distance of my theta, or my angle. If it is in the third quadrant, I'm going to take 180 plus my theta. If it's in the fourth quadrant, I'm going to take 360 minus my theta, which is what I did on this. Now, here's another way of doing this, okay? I already know what my component form of this is because I already figured it out. So my component form was 2, -8. So if I were to graph the vector that lines up with 2, -8, so here's 2, -8, 5, 6, 7, 8, it's going to be down here. I think I'll do it in green, okay? Okay, so let's say we're talking this point right here. Okay, there's my vector. Okay, so you can see that my vector is in the fourth quadrant. So what I'm trying to find is I'm going to try and find this angle right there. And I found it up here. It was 76. But because my vector is in the fourth quadrant, I'm going to take 360 minus my 76, and that's where my 280 came from. If you will, this is your cheat sheet. Okay, let's do another one of those. That's probably the hardest part of this section. All right, so here's another one. Okay, I can do my component form first. That's probably the best way to do this. So remember, tip to tail. So it's -4 minus 2. And it's going to be -1 minus a -2. So this is going to give me a -6, and that's going to give me a +1. Okay, so that's going to be my component form. I can find the magnitude by plugging this into the Pythagorean theorem. So if you will, m is equal to, or m squared is equal to -6 squared plus 1 squared. So that's going to give me a 37 right there. So the magnitude is equal to the square root of 37, which you can take your calculator and get a decimal form for that. Square root of 37 is going to give me 6.1 approximately. Okay, so there's the magnitude. That's one thing I needed to find. The other thing is the direction. Now, if I took this thing and I took my component form and I drew a standard position vector, then I'm going to go -6, +1 is going to be this point right here. So that's going to be that vector shifted up here so that the tail of it is on the origin. Okay, now I want to find out what this angle is. So this is a 1, and this would be a 6. So I want to do, and that's a -6, if you will. I want to do inverse tangent of opposite, which is a 1, over adjacent, which is -6. So inverse tangent of 1 divided by -6 is going to give me a, well, let's do it positive because I think that'll be the easiest way. Hold on. Okay, so I'm going to get, don't worry about the positives and negatives. We'll keep them all positive. So I'm going to get an answer here that angle, theta, is 9.5. Now, if you go back to your cheat sheet here, if it's in the second quadrant, which it is, I'm going to take 180 minus my 9.5. So 180 minus 9.5, it's going to give me a magnitude, a direction of 170.5 degrees. And that's exactly, that angle right there would be 170.5. It's 9.5 short of the 180. All right, vectors can also be added. So let's say I was going to add the m and the n together. You just add their components. So the answer here is -4 plus 0, which is -4. 5 plus -10 is -5. So when I add them, that would be my answer. Vectors can also be used in translations. Let's say I want to take this image, A, B, C, and I want to do this translation under the vectors M and N. So the first thing I want to do is I want to add them together. So my new vector is going to be 1, 2. Okay, so I added the x's and I added the y's. So then I know that I'm adding 1 to the a and 2 to the y, or 1 to the x and 2 to the y. So a prime is going to give me -1, -1. B prime is going to give me 1, 4. And C prime is going to give me 2, +1. So when I go to graph this, I have -1, -1 is my A prime. I have 1, 4, which is my B prime. And I have 2, 1, which is my C prime. So you can see that I translated this or moved it based on those two vectors, which meant I added 1 to the x and 2 to the y. 9.7 is it was about transformation matrices. Matrices can be done with any of the 4 transformations that we discussed, but I suggest that you only use them for the rotation, but that's entirely up to you. Make sure you have the rotation matrices entered into your calculator. Okay. Your review homework is on page 313 through 513 through 516, 10 through 20 even, and 28 through 46 even.